Welcome back to Chem 101. We're going to be looking at Chapter 4, Reactions in Aqueous Solution. So we're going to focus our study of chemistry on a particular kind of chemistry, water-based solution. That's what aqueous means. First thing that we need to do as scientists who like to take measurements and record observations is make sure that we have a set of units that will work for the kinds of measurements we want to be able to make. And so when we talk about a solution and how concentrated or diluted it is, we want to be able to put numbers to that. And there are several kinds of concentration units that chemists use, but the most common is molarity. And the definition of molarity is the number of moles of solute molecules or ions or formula units divided by the number of liters of solution. And once we've agreed on that as a concentration unit, then we have an equation that will help us anytime that we want to take a very concentrated solution and dilute it down by adding water. If we have a particular molarity that we know of our stock solution is very, very concentrated, a high molarity, and we want a lower molarity, and we can call that M2, and we want a certain volume of that lower molarity, then we can calculate, solving for V1, the number of liters or milliliters of the original concentrated solution we would need to start with in order to get that concentration and volume. The key to this equation is that the units be the same on both sides. We use molarity here and molarity here. We can use milliliters here and milliliters here, or liters here and liters here, any volume unit we want, as long as they're both the same. And so what I want you to do is give this a shot on your own. I'll give you a couple of hints. Pause the video, write this down. What is the molarity of a solution made by dissolving 2.355 grams of sulfuric acid? So we'll need to convert that to moles to make our numerator. We'll do that using the periodic table and this formula. In water and diluting to a final volume of 50 milliliters. And again, we're going to have to convert that unit to get our denominator in liters. One of the key terms in solution stoichiometry, and we're going to spend more time dealing with this in the lab than in the lecture part of the course, but I want to get the definition out there. Titration is a procedure for determining the concentration of a particular solution that we don't know. We put some of that, measure a certain amount of that perhaps into a flask, by allowing a carefully measured volume that would be in our flask to react with a solution whose concentration we do know very, very well, and to a high degree of accuracy and precision. Quite often we would take the solution whose concentration we do know, and put that into our burette, and then we would allow that to flow. We've done a titration already. We'll do another one this semester, and those of you who move on to Chem 102 will do several next semester. Here's another mathematical example I want you guys to try out on your own. We can buy HCl and have it shipped here to the university at 12 molar solution. Quite often when we buy solutions, we buy them at very high concentration, higher than we need for most of our experiments, because it's cheaper to ship them that way. The more the solutions weigh, the more we'd have to pay to have them shipped here, so we don't want to pay to have water shipped here when we can get our own water and water solutions down. So the question is, how many moles of HCl would we have in a 300 milliliter sample of this solution? So try to work that out. Remember, this is moles per liter, and the volume you have here is in milliliters, so you may have to do a conversion to get all your units to cancel and to get moles. Some important types of compounds that we can find are electrolytes. Some compounds, and this is something people don't necessarily realize, water, pure water by itself, does not conduct electricity. Water only conducts electricity once there are electrolytes dissolved in it, and tap water has some electrolytes dissolved in it. For example, look what happens with the sugar molecule. If we dissolve sugar, this is table sugar, sucrose, C12H22O11. We dissolve that in water, we get a solution of individual molecules of sugar, no charges, and that's not going to conduct electricity. But when we dissolve an ionic compound like table salt, sodium chloride, in water, the sodium and the chloride ions separate in the water, and they are individual charged particles. When we have charged particles in solution, ionic compounds, acids, bases, that's when water conducts electricity. So electrolytes are defined as compounds that dissolve in water to produce electrical conduction, to make the water able to conduct electricity. Salt is an electrolyte. Sugar, then, is a non-electrolyte. It dissolves in water, but there are no ions after it dissolves. Salt is what we would consider a strong electrolyte. When it dissolves, every formula unit of salt breaks down to ions. A weak electrolyte, and a lot of acids and some bases fall into this category, will dissolve completely in water, but not all of the molecules separate into ions. Maybe 90% of them act like sugar here and stay together, and only 5 or 10 or so percent of them break apart as ions. So a 1 molar solution of sugar won't conduct electricity. A 1 molar solution of salt will conduct electricity very well. And a 1 molar solution of a weak electrolyte like acetic acid, which we find in vinegar, will conduct electricity a little bit, but not nearly as well as the salt solution. Here's an example of what I mean. We've got a light bulb hooked in a circuit with a battery that's kind of off camera here. And in order for the electricity to travel and light the light bulb, it has to go through this water solution. In this water solution is sodium chloride. And we have ions, and that allows for electricity to be conducted. In this water are no ions. This is a solution of sucrose, and there's no charged particles, no ions. Same battery, the light doesn't light. There are 6 strong acids. Those are acids that behave as electrolytes, as strong electrolytes, that every molecule breaks down to ions. HCl, HBr, and HI. That's hydrochloric, hydrobromic, and hydroiodic acid. Perchloric acid, hydrogen perchlorate, and nitric acid, and sulfuric acid, all strong acids. Other strong electrolytes are any other ionic compounds, any compounds that have a metal as their first element that are soluble in water. We'll talk about solubility rules a little bit later in this chapter. Weak electrolytes are any other acids. The most common that we'll talk about are these two, but there are a lot of other acids that are weak acids. These 6 are the only ones you have to consider acids as strong acids, unless you're told otherwise. But alcohols and sugars and water itself and most other organic compounds are non-electrolytes. And we'll do a lab to illustrate and practice some of this in the next couple of weeks. Now we want to look at several different kinds of chemical reactions that occur in aqueous systems. Again, by aqueous we mean where water is the solvent. A precipitation reaction would be what we would see if we take 2 solutions where the ionic compounds in both solutions are dissolved in water, but when we mix them, the mixture of ions generates a compound that's not soluble in water, and so a solid comes out, and we consider the solid to have precipitated, and that's a precipitation reaction. An acid-base reaction is one where a compound that can provide a hydrogen ion, what we call an acid, reacts with a compound that consumes hydrogen ion, which we call a base, and the product generally is some sort of ionic compound, which we call a salt, and water. That's an acid-base neutralization. And then a redox reaction or oxidation-reduction reaction is one where one particular atom or element exchanges electrons with another. It gives up electrons to another, or it takes electrons from another. And we'll define some terms associated with that in the next few slides. We like to be able to write chemical equations for all of these kinds of reactions, and there's several kinds of equations we can write. The kind that we've written and balanced in class so far, for the most part, are what we would call molecular equations. We write down the full molecular formula or formula unit in the case of ionic compounds for each compound in the reactants and the products, and then we balance the equation. An ionic equation, though, instead of writing the formula unit for ionic compounds or for strong acids, writes those as separated ions. So a reaction in which HCl was involved, we wouldn't write HCl. We would write H plus and Cl minus. A reaction in which KBr, potassium bromide, was involved, we wouldn't write KBr. We would write K plus as a separate entity from Br minus. Now, what we'll notice when we write these kinds of equations in a lot of cases is that there are what we call spectator ions. There are ions that are listed on both sides of the equation that don't change form. They're listed on both sides of the equation as separate ions, and they don't change or become part of new compounds or break off from anything. And if we write a net ionic equation, then we're taking the ionic equation and we're crossing out or erasing all of the spectator ions. We're only showing species in the equation that participate, that undergo changes. And we'll notice if we do this correctly, the equation will stay balanced throughout the process. Now, here's an example of a precipitation reaction. Lead nitrate is soluble in water because all nitrate compounds, metal nitrates, are always soluble in water. Potassium compounds are always soluble in water, so potassium iodide is soluble in water. But if we mix these, there are potassium ions and nitrate ions together. We say they're always soluble, but there are also lead ions in the mixture and also iodide ions in the mixture. And lead iodide is not soluble in water. So if we want to rewrite this equation as an ionic equation, any ionic compound or strong acid that's shown as aqueous will separate into ions. So instead of writing lead nitrate this way, we'll write lead 2 plus and 2 nitrate ions. Instead of writing 2 potassium iodides, we'll write 2 potassium ions and 2 iodide ions. In the products, instead of writing 2 potassium nitrates, we'll write 2 potassiums and 2 nitrates. But lead iodide is a solid. It's not dissolved in water. It's not separate ions. So we leave that together. So now if we want to write a net ionic equation, we'll notice the 2 nitrates didn't change. The 2 potassiums didn't change. So in the net ionic equation, we'll leave those out and just write the ions that are left. Lead react with iodide to make lead iodide. The potassium and the nitrate were just there to help get the active ions into solution. They stayed in solution. They didn't change form. They're not shown in the net ionic equation.